provide a counter example to justify each of the following false statements. So here we got, if W is a linear combination of U and V in R3, then U is a linear combination of V and W. So we say U is not in general. So let's write down W a linear combination of V and W in R3. So let's take W be 2, 2, 2 equals, I can have 0 times U. I'm going to write 1, 2, 3 plus 2 times 1, 1, 1. Okay, so this is W, U, V. I just wrote W as a linear combination of U and V. Okay, 0 times this is 0, and now we have 2, 2, 2. But this U, 1, 2, 3, okay, this is nothing. This is not equal to any constant like 2, 2, 2. We multiply by a constant and another constant, I don't know, 1, 1, 1. Okay, these two vectors, no matter how hard we try, not gonna give us 1, 2, 3, because 2, 2, 2, 1, 1, 1, they're gonna lie in the same line kind of, and then this is not the case. Okay, 17. Suppose V1, V2 and V3 are in R5. Okay, V2 is not a multiple of V1, so V2 is not multiple of V1, and V3 is not a linear combination of V1 and V2. So V3 is not. Then V1, V2, V3 is linearly dependent, so linearly independent. So we want to make it false. That means we need to create V1, V2 and V3 linearly dependent. So let's write down V1, V2 and V3. So V1, okay, V2, V3 with these properties. V2 is not a multiple of V1. Okay, so when we write V2 is R5, so we have 5 components here, we have 5 components here, and we have 5 components here. Okay, V2 is not a multiple of V1. Pretty much the whole idea is, if we have one of the vectors 0, 0, 0, then we always get linearly dependent, right? So we can say 0, 0, 0, then fine, then we can have like 1, 1, 1. Okay, now V2, this is not a multiple of V1, so if we multiply by any number, we never get 1, 1, 1. That's true. And V3 is not a linear combination of V1 and V2. So if I write, here's 1, 1, 1, if I write, let's say 1, 2, 3, then 1, 2, 3 cannot be written as a linear combination of these two. I mean, this one has no contribution because all zeros. And here, if we multiply by 1, we can match this. Multiply by 2, we can match this, but we can never get this. So these three vectors satisfy these conditions. But V1, V2, V3 is linearly dependent. Why? Because V1 is a 0 vector, and we know that in a list of vectors, if one of them is a 0 vector, then that set is always linearly dependent. The transpose of a product of matrices equals the product of their transposes in the same order. We know it works in the backward. What is true? When we have a product of matrices transpose, if we take transpose, that is, it's in backward. That's true. But this one is claiming A, B, T is A, T, B, T, which is false. So we just write down two matrices and done, pretty much. Okay, you can come up with some matrices, I don't know, easy, 1, 2, 0, 1, and and let's say B is what? Okay, and then you can write down anything, I don't know, 1 1 1 0. Now we are trying to find A times B, then A times B, let's multiply A and B. So A and B means we multiply this to this. Okay, let's make it 0 so that the calculations will be easier. Okay, here is 1 2 1 0, that just gives 1. This one times this one, 1 times 1 plus 2 times 0, and this one times this one gives us 0. Okay, now 1 2 times 1 0 is just 1, and 0 1 times 1 0 is 0. So that's the AB, and we can now find AB transpose, which is 1 1 goes here and 0 0. So we find these two and multiply. What is A transpose? A transpose is 1 2 and 0 1. Okay, and B transpose is, so I'm going to write here 1 1 here and 0 0. So pretty much I just wrote here A transpose times B transpose, A transpose times B transpose, and I'm trying to show this this matrix will be different than this. AB transpose is not equal to A transpose B transpose. Let's multiply 1 0 1 1, that's going to be 1 2 1 1 1. Okay, 2 1 1 1, 2 times 1 2, 1 times 1 1, 2 plus 1 3. Yeah, already different, right? 1 0 0 0, that's 0, 2 1 0 0 0, but these two are not the same, not same. Okay, so not in this order, same order. If we flip the order, then it works. 19. If A is a non-zero matrix and AB equals AC, then the matrices B and C are equal. What do we think? AB equals AC, we multiply by A inverse, then this will be identity matrix. This is identity matrix, so we get B over C. I mean, that's true if and only if when A has an inverse. Okay, but if A is a singular matrix, not invertible matrix, then we cannot multiply by A inverse. So that's why this is false in general. I mean, this is true if A is non-zero invertible matrix, then this is true. So let's do it. Let's say A is 1 1 2 2. Now you can take B and C, anything, I don't know. B is, so A times B should be same as A times C, right? So, and now we need to come up with good examples here. So we need to think carefully and see. So when we multiply A and B, that should be same as A and C. Let's take, I don't know, this one is tricky. So 1 1 0 1, and I'll come up with C. So then what is A times B? A and B, if we multiply 1 1 1 0, we get 1 2 2 1 0, just 2, 1 1 1 1, that's 1 times 1 1 plus 1 2, 2 2 1 1, 2 plus 2 4. Okay, now A and C, when we multiply A and C, we have to get the same thing, 1 2 2 4, but C should be different because that equal, that's false. So we want to make, so come up with some matrix so that when we multiply A and C, it got to be there. So 1 1 0 1, how about writing this one 1 0 1 1. Obviously B and C are not the same. Let's see if it works. 1 1, if we multiply 1 1 1 1 1 1, here is 1 1, that's 2, not working, so this is not a good choice. Okay, how about writing this way? Let's make this is 0 1. Okay, let's see. Obviously B and C are not same, because now 1 1 0 1 1 1 0 1 is 1. 2 2 0 1 is 2. 1 1 1 1, that's 2. 2 2 1 1, that's 4. Yeah, so A times B and A times C are same, but B and C are different. The whole idea, A is a singular matrix. This matrix does not have an inverse. Okay, final.